For the last week or more, we've been talking about fuel cells as a black box, something that produces electricity, produces thermal energy, and we're doing heat and material balances on it. What I wanted to start doing now is like opening this box that I'm calling an SOC stack or a PEM FC stack. What's inside that? And what are some of the complexities and issues in designing the stack itself that relate to problems in chemical engineering? From a stack design standpoint, there are two approaches people have taken to try to design a stack. One of them is to try to keep the manifolding simple by building all the complexity into the cell. In the SOFC world, anyway, this has led to trying to design things with tubes. The basic idea of a tube cell, we make our cell round. You have an electrolytic tube, and we put the one electrode on the inside and one electrode on the outside. We take the outside of the tube and we paint the anode. It's more complicated than painting, but for the moment, I'll think about it that way. And then on the inside, we place the cathode. And this is designed in such a way that I can get some through electrical conduction from the outside of the tube to the inside of the tube from the next tube down the list. So I've got cell 1, and then underneath this, we put cell 2, and then cell 3. Got a bunch of cells. And for it to work, the anode of one cell has to be connected to the cathode of the other cell, just like two batteries stacked on top of each other. But imagine this is now circular batteries where the electrode's on the inside. We've got to somehow make connection to the inner electrode and connect that to the outer electrode of the next cell down the stack. So we have some type of through connection through this cell to what's called the interconnect, and it makes contact to the next cell. And then there's another connection to the next cell, and so forth. To make this work, we've got to somehow be printing this stuff onto these tubes with this complex geometry that, in the case of the anode, only goes partway around the cell. We've got to have some kind of through connection between the inside and the outside of the tube along the length of the whole tube. So right away, I think you can sort of see this is going to be kind of complicated to try to figure out how to make the cell. It's a complicated cell. But in terms of stack design, wow, super simple. And the reason is you could take each of these tubes and, it ends up kind of looking like this. I have fuel on the outside, and then we literally have a tube running down into this thing. It comes from a plate. It's welded to a plate somewhere. So we have air. We have an air manifold. The air goes into the tube, goes down the tube, reaches the end of the tube, and it's distributed and goes back up the sides of the annular space between this inner tube and the fuel cell tube, the fuel cell. You have air on the inside. So air's on the inside, fuel is on the outside out here. And you have another manifold right here where the unused air escapes and the fuel that you are not used up yet also escapes, and then it burns in here. So you have a manifold for air, you have an exhaust manifold, which also serves as the afterburner, and then you have these tubes. And so if you think about the sealing surfaces you have in the system, there's only one seal in the whole thing. The tube actually sits loose in its manifold because it's just connected to the afterburner. The only seal in this whole thing is where the air tube is welded to a plate. It's like a hole in the plate with a circumferential weld in it, just like, a shell and tube heat exchanger. So this is the one and only seal in the whole thing, which is fantastic because these things are hot, right? It's high temperature. The tubes can expand and contract. There's all kinds of thermal stresses you could imagine having, which you don't worry about because the thing can just grow and shrink with temperature. It's beautiful, right? The cells just sit on top of each other pretty much under gravity. They're connected to each other with these interconnects. It's a little bit more complicated than I'm making it out to be, but um, from a stack design standpoint, it's almost trivial. Um, why don't people do it anymore? It's just too expensive. You can't manufacture ceramic components with these sort of three-dimensional features in them um, cost effectively. It just doesn't work. Um, Everything that's made cheaply today with any kind of complex patterns in it, those things are done with top-down manufacturing processes where you have things on an assembly line and you spray stuff on it or irradiate it with things or put masks down and everything is just, you know, you're doing something on a flat surface. Um, that's how we've come to be able to make electronics super cheaply. So that's the short version of the problem. Manifold, you know, if you have a manifold that's simple and a cell that's complex, it's way too expensive. So the way the industry has moved, both for PEMs and SOFCs, this is a universal trend, has been away from complicated cells to try to make the cells as simply and cheaply as possible. So with planar geometry, where basically we want to make cells by cheaper roll to roll or flat plate deposition processes, and then stack them up into a stack. So these are all flat plates. They're stacked in some way. So basically, in comparison, here the cells are very simple. But now the stack and the manifolding, that's the part that becomes complex. If you just think about the gas distribution, just forget the electrical interconnections or any of that stuff just for a moment. Think about what we have to do. We have to make these cells, we have to electrically connect them so they're all connected to each other at every point so that it can easily transfer current from one cell to the next one over its entire surface. And then at the same time, we have to distribute air all on one side of every single cell, and then we have to distribute fuel on the other side of every single cell, you know, and it's even hard to actually draw what that even looks like, right? Because we've got to have, let's say the cathodes are on the bottom of all these cells. So on the bottom of each cell, we're feeding air. That means that along the top of each cell, we've got to feed fuel, right? And how do we do that? If we're already feeding air on one side, how are we going to arrange that, right? So one of the simplest things people try to do is stack up these cells and then have just little holes in the side, right, where the gases would go in, and then the air would go on one side, and then the fuel you would feed in this way from this side. So the air would go on the bottom, the fuel would go over the top, and it would come in from the left, whereas the air comes in from the front, right? And so from the top down, it looks like this. You're feeding fuel, and then out this way is the depleted air, something like that. But even that gets pretty complicated because you might have holes, right, on each side of the cell that are staggered. You know, every other hole is an anode or cathode hole, but then you've got to have some kind of manifold or cap that sticks on the side of the stack to kind of like cover the entire outer surface of the stack, and be able to keep that under air pressure, right, and seal around that. And you know, your manifold material has to have the same thermal expansion as the rest of the stack, so it doesn't crack when the stack expands and contracts. Every single cell has to be sealed around its entire perimeter, basically to keep the gases inside and connected just to this one cell it's next to and not leaking out. So we got all kinds of things, right? Seals. the manifolding of the air and fuel. We have electrical distribution. And the problem there is most of these electrodes are super thin. So it's not good enough to just touch them in one spot and then expect them to be able to carry all this current in a uniform way. The problem is once current hits a cell, it's got to spread out. And you make bigger and bigger cell you make, the more that current has to spread out over the entire electrode. Unless that electrode becomes super thick that you can easily conduct current laterally, then it becomes harder and harder to ensure uniform current density. So usually what developers try to do is, even if the electrodes are not perfectly conductive, you'll have some layer of material that acts as a current collector that can help distribute the current. And then you try to make contact at many, many, many points. So the current, as it comes down from one cell to the next cell to the next cell, it's not being bottlenecked in any one spot. You're basically trying to maintain a wide uniform current density across the whole cell as it passes current to the next cell. Another issue is thermal or chemical expansion. In SOFCs, it's mostly thermal expansion and contraction as this thing gets hot or cold. In PEMs are expand and contract a lot with humidity. So as you put water into them, the polymers can expand. It can cause them to buckle and dimple. So we have to be careful about how this whole thing is put together in a way that when it becomes humidified, we're keeping everything flat. And then we also have to make contact all these cells uniformly everywhere. So there's the problem of conformal contacting. One more is fluid mechanics, fluid pressure drop and things like that in the flow channels. So these are just, some of the issues that we're dealing with in stack design.